The particle moves in a straight line so that its velocity at time t is given by the function v of t equal to 12 minus 2t feet per second. We're asked to find the displacement of the particle over the time interval 0 to 8. So when we're asked to find the displacement, what we're calculating is just the net change in the position. So this doesn't depend on the path that my particle takes. So in the picture here, I can travel out along the green arrow, I'll turn around at some point, and then I'll travel backwards along the blue arrow. And wherever I end up at time t, I'm just measuring the length of that leftover portion highlighted here in blue. Okay, so now the distance is slightly different in that it depends on the path that my particle takes. So if I travel out 10 miles and then I travel back, say 5 miles, the distance is going to be 15 miles, but the actual displacement is just going to be 5 miles, right? So to calculate the distance, I add up the length of my trip out and I add the length of my trip back, and I put those inside of absolute values because, again, if I'm traveling backwards, it's going to have a negative sign attached to it. And so I want to add up just the magnitudes of those trips. Okay, and now we can see that the displacement is just given by the position at time 8, and we subtract the position at time 0. The problem in this case is that I don't know anything about the position function. All I know is that the velocity is given by v of t, and I have an explicit function given here in the problem. Okay, so what I want to use then is I want to use the net change theorem, which says if I want to integrate from a to b, f prime of x dx, that's just equal to f of b minus f of a. Okay, so now what I'd like to do is then relate the position function with the velocity function. And we can do that by just recalling the simple fact that v of t is the derivative of the position function with respect to time. Okay, so now that I have this, I can go ahead and apply the net change theorem to calculate the displacement. Okay, so finding the displacement over the time interval 0 to 8 is the same as evaluating the integral of v of t dt, which is the integral from 0 to 8, 12 minus 2t dt. All right, so that gives me 12t minus t squared, evaluated from 0 to 8. That gives me 96 minus 64, which equals 32 feet. Okay, so the displacement of this particle is 32 feet. Now let's also go ahead and calculate the distance so we can see how that differs. The main difference in calculating the distance versus the displacement is that I need to figure out when my particle turns around. So in the example that I have here, I need to know at what point in time my particle starts to turn around so that I can break the interval that I'm integrating over into two separate portions, one where I'm traveling away from the origin and one where I'm traveling back towards the origin. Okay, so to do this, I need to take my velocity function. Let's say we're finding distance. I need v of t to be equal to 0. So in other words, I need 12 minus 2t to be equal to 0. And that happens if and only if t is equal to 6. Okay, so I know that my function is traveling out up until t is equal to 6, and then it starts to travel back towards the origin after time is equal to 6. Okay, so to calculate the distance, I integrate from 0 to 8, 12 minus 2t. But I need to break this up into two separate integrals, one where I'm traveling away from the origin, so that's going to be my integral from 0 to 6, 12 minus 2t dt. And then the second integral where I'm traveling towards the origin, and I'm going to put that inside of absolute values. So from 6 to 8, I'm traveling towards the origin. And now I just need to go ahead and evaluate. All right, so if I evaluate this term here, it's going to give me 36. The second term is going to give me, inside of absolute values, a negative 4. And so altogether, we get 40 feet for the distance.